there's a couple of criteria that a quantum system has to fulfill to be useful for quantum computation and then also to be useful for quantum communication. These basic principles have been boiled down by David DiVincenzo and Daniel Loss in the DiVincenzo laws or DiVincenzo criteria. While I was still working in the research center and doing my PhD, I actually had the pleasure to meet Professor DiVincenzo in a couple of seminar sessions and so on. So that's definitely something that kind of stuck to my mind and that I want to talk with you about in this little basics video. So let's start with the DiVincenzo criteria, and the first one is about the scalability of quantum systems. So a scalable physical system with a well-characterized qubit. So what does that mean? In order to understand this, let's take a step back and dissect this sentence into its specific parts. So first of all, we have the scalable part, right? So the system needs to be scalable. You cannot just have a single isolated system. It should be a scalable physical system. That's important because if you want to build a quantum computer, obviously one quantum bit is not enough. As for a classical computer, a single bit is not enough to build a computer, right? So if you, for example, think about an ion trap quantum computer, it's not enough to trap a single ion and use that, but you actually need to have multiple of those lined up, for example, in an ion chain. The same is true for the chip-based quantum computing approaches, right? You need to have a couple of those. For neutral atoms, you need to line them up in this crystal structure, 2D, for example, to actually create a quantum computer, right? So you need multiple quantum bits, and for that you need an approach that is scalable. A very classic example in the past that has worked well, proven to not be scalable enough, was the NMR-based approach. So you would use, for example, molecules that have several atomic states, like electron states, that you can use to build qubits. You can actually scale that. So within a single molecule, you can have multiple of these qubits built in. However, it's not infinitely scalable because we don't have infinitely large, or well, it's not scalable until a certain point because we don't have molecules that are getting bigger that you can still control and where you can still access the quantum states. So that's about the scalability part. The other side is the well-characterized qubit. And for that, let's think about how to actually create a qubit. So a qubit is usually built into a two-level energy system. So think about, for example, an electron that sits within an atom. You have these different orbits that can be visualized by different electron trajectories around the nucleus. Now, in fact, this is not a physically fully correct representation because in quantum physics we talk about the wave states of the electron, right? About the wave functions of the electron, which then kind of lead into the probability function, so the probability density more or less that you actually have. But let's take this complexity aside. We have the electrons that can jump up these different levels. And usually these levels, they are based at different energies, right? So there's a jump from, let's say, we have an electron in a, I don't know, in an helium atom, when you have basically the S band filled up. So both of these electrons spin up and spin down. They're sitting in that band. Now, in order to excite one, you can excite it into a P state, into a D state. So these are the different orbitals. And the distance, the energy distance between those excitations is usually unique. That's, for example, why in specific emission spectra, we always have these very specific let's say light frequencies. For example, for lasers, they only shine one specific light frequency. That's because the level distance where you get the transition that produces the photon, the light of the laser, that is a very unique energy. And vice versa, if you're, for example, looking at the sunlight from the Earth, if you're looking at, let's say, the light that we receive from the sun, you will see that it's not a full rainbow. And that's not because the sun doesn't emit a full rainbow. It actually does because it's emitting, basically due to its heat, a full spectrum. But actually what is happening is, due to our atmosphere that we have around the Earth, our gas atmosphere, we have specific absorption line. And if you're looking at it at a very, very, let's say, high resolution at the color spectrum, you will see that there are like dark like black areas, like lines in this emission spectrum. These are called Fraunhofer lines. And they are there because our atmosphere is absorbing specific light frequencies because the molecules and atoms, they're absorbing specific frequencies. And that's, by the way, for example, also why, for example, CO2 is a problem potentially for the atmosphere, because you have these vibration grades that have very specific frequencies, and now you are, let's say, you have a certain absorption in a specific vibration in a specific infrared wavelength. But that's for a different time. Now this is, let's say, the first criterion, right? Why do you need to have these well-characterized states? That's maybe also important. Well, if you, for example, think about your qubit and you want to switch it from 1 to 0 and vice versa, you want to make sure that you only cater to this one specific frequency and not to any other. Like if you, for example, had a perfect well potential, so let's say an electron that sits in a box, then the excitation levels that you have, because of the potential well that you're building, they are usually equidistant. So you go by specific levels, and you can only, they are all at the same distance. So you cannot differentiate the transition between 0 and 1, 1 and 2, 2 and 3. They all have the same energy that is associated with, which makes it difficult to get your system back to the ground state, which already leads us to the second principle, which is the ability to initialize the state of the qubits to a simple fiducial state. So basically creating a ground state that you can start with that is well defined. For example, putting all electrons to the lowest energy level, or putting all qubits to 0 state, right? And now the next thing, and I mean that kind of makes sense, right? Because you need to have a definition of where you actually start when you start your algorithm. Otherwise, you're ending up with something random if you don't even know how to characterize the system in the first place. Now, the third one is very interesting. It talks about the coherence time. So long relevant coherence times. What does that mean? So coherence time is the time, more or less, that a state can basically persist or keep its quantum information. Think about, again, our electron that's getting excited to an excited state. So putting, for example, the electron from the s orbital to the p orbital. Now the question is, how long can it stay there? What is the coherence time that it can have? And this can have various different factors. Of course, there is maybe a tendency of the system to fall back to its initial state. However, that doesn't necessarily have to be the case. Now, the system itself is usually not fully isolated from its environment. So usually there are some ways for the environment to interact with your system. And that's what can cause coherence. So think about an electron spin. An electron spin is a magnetic property of an electron. So the electron spin can point up or down, let's say, or we have a measurement that can project our quantum state into the up or into the down state. Now, thinking about that, let's say we have an electron sitting within a silicon cube. Now we are bringing that to a defined up state. There are actually a lot of nuclei, so the cores, the nuclei of the atoms that are sitting around this specific electron that might have some net magnetic property. So looking at them from the outside, they're not exactly 0, but they're pointing into some direction. And because of temperature, they might also be fluctuating, changing their directions. Maybe there's some external magnetic field, maybe some cosmic radiation that is kind of passing by, like high energy particles like muons, which are basically like electrons, heavy electrons that are passing by and that are causing some kind of disturbances. And all of these factors, they can now influence our electron that we prepared maybe in the up state to flip back down to the ground state, to the down state. So think about, for example, a magnet where you align all of the magnetic domains, and now you would be able to switch one of those domains into the other direction. There's always a force that kind of wants to flip it back, and that's kind of a semi-stable state. So unless you give it a little bit of a bump, it will not flip, but at the moment where you kind of excite it, where you put a little bump into it, it falls back. And I mean, this is always the case with every kind of system, right? Whenever you have some energy, the energy tries to dissipate into all the different degrees of freedom. Think about your pendulum. Think about Newton's cradle. You know this little setup where you have like 5 balls, they are all lined up, and now you're taking one of them, you're letting it go, and then it bumps against the sitting balls, and one of them is going into the other direction, right? Now you have some energy that is sitting in this system. So there's some, let's say, potential energy. So when you take the ball like this, you create potential energy, you let it go, this energy transforms into motion, so kinetic energy, then bumps into the balls, takes the momentum and hands it over to the other ball, and that one again does this move from kinetic energy to this potential energy and back and forth. But actually, if you're looking at it, it doesn't always do exactly that. Now the balls, they start to move in this direction, so you see that there is not a perfect line anymore, but there's like some misalignment. Maybe the cradle doesn't swing exactly in the right direction, so you see the energy is dissipating. It's changing or it's moving into all the degrees of freedom. And the same thing is also happening when you're looking at these small quantum systems, just with the difference that all the information is being stored in this very, very tiny energy state, right? In the smallest possible excitation, the quantum excitation of your electron. And now, of course, you cannot, let's say, spare a lot of that energy, because as soon as you're losing this energy, you're basically losing your information. There's no extra energy to spend on, right? And this is kind of what we see when we talk about this decoherence. Now, there is a difference between the relevant and the non-relevant decoherence time, right? So what do we mean by that? Let's say you have a quantum computer and you want to generate, you want to do some operations on this, right? You want to, let's say, flip a qubit, do something with it. We will talk about that in the next step. Now you want to perform some steps within this algorithm. Think about your classical computer. You have bits. You're performing an AND gate, an NAND gate, an OR gate, a NOR gate, whatnot, right? A negation of your bits. So you're performing different operations to basically create the algorithm. And the same is true for the quantum computers. You're doing different gates. And now what is important is you need to be able to perform enough of these gates before you are losing basically the quantum information, before the quantum information feels too much of this decoherence and it's basically lost and it ends up in a random state. So you need to be able to perform enough of those gates, and that's an important threshold that we always need to keep. So there might be systems that have a very, very long coherence time, like for example an NV center in a diamond can have a very long coherence time. However, it is kind of difficult to switch this state, to do some gate operations, to kind of entangle this to something else. So there the coherence time versus how much time it actually takes to transfer quantum information is maybe not ideal. In another system like a superconducting qubit, you might have only a very short coherence time, but that's not such a big problem because anyways you're operating with gates on radio frequency, so at a very, very high frequency, so you can perform a lot of gates at a very small amount of time, and it might even be good enough to actually run some algorithms on that. And that's basically what different companies, we've seen IBM pioneering that, let's say, in the commercial field, but then also Google, for example, showing a lot of great results on this. What they've been showing is you can run enough gates within the decoherence time to actually do something with those machines. There's a debate whether what you can do is meaningful or not. That's for a different video, but that's one case. Another one is, for example, with the ions. We've seen ion qubits that can be used to perform specific operations. Here, the speed at which these operations are happening is much smaller. It's much smaller, so it takes longer to do these operations. But at the same time, it's not a problem because the coherence time that these systems have is higher. So that's the point about the relevant quantum coherence time, right? Now, the next one is about the universal set of gates. And that's kind of similar to what you know from classical computers. There's like Turing complete systems and stuff like that, where you basically try to attribute a level of capabilities, of powers, to a specific compute platform, to a specific compute architecture. So if you only have maybe one single operation, you can flip a bit from yes to no, from 1 to 0. You can potentially do something with it, right? There could be some application to work with that, but for sure you cannot do everything with it. You cannot build arbitrary algorithms this. So a single gate is not enough, or the specific single gate that I was talking about is not enough to basically build the whole algorithmic landscape on that. For that, you need to have these so-called universal quantum gates. There's a set of those. Actually depends on what kind of platform you're looking at. It might be different. There are the Clifford gates and so on. And if you're interested in that, make sure to also subscribe to this channel so you don't miss out on the video which might be talking about the total amounts of gates or different gate sets that are usually being used in those quantum computing. Now let's talk about the last one, and this one, the fifth point, is about the measurability. So it says qubit specific measurement capability. So what do we mean by that? Well, we have initialized our system. We have well characterized qubits, right? Now we are doing some operations on them with our gates. They remain in the coherent section, right? So the quantum information is not getting lost. But of course, it makes sense that at the end you need to be able to read this out. So you need to be able to project the actual state that the quantum system is in into a 1 or a 0. And that's what this point is referring to. So it is about being able to map the quantum state or the state of the system onto a 1 or a 0 in terms of the quantum state. And that's of course qubit specific, so that might look very different for an ion qubit compared to, for example, a spin qubit, and for a superconducting qubit. So there are different platforms, right? We talked about those, and they all have their various different ways of initializing the system, manipulating the systems, or running those gate operations, and then of course also about the readout of those. Now these are the 5 criteria. There's another 2 that are relevant when it comes to quantum communication. So the first one is the ability to interconvert stationary and flying qubits. And that is basically you have some qubits stationary that you're using to store and to process quantum information. So something like a quantum memory. If you're searching for this, you will find a lot of activity in this area, as well as a processing space, right? You might want to process this quantum information. You might want to do some manipulation to that before you're actually reading it out. And then, of course, the flying qubit. So that's the messaging qubit. That is, for example, your photon that you're using in order to transfer certain quantum states, right? Then the other thing is and the important thing is that you need to be able to convert these into each other, right? Now you might say, okay, you can have something like a little photo detector. Yes, but you also need to be able to extract the quantum information, right? You want to, for example, know the polarization. So you need to have a polarized photo detector to read out, but maybe you want to store the information or to process it, right? And then you need to be able to kind of map a photon into, for example, an electron state or something like that, or vice versa, to be able to create from an electron state that is, for example, spin up a photon that is polarized, circularly polarized in one direction or in the other, or that is horizontally polarized either in vertically or horizontally polarized, right? And there the difficulty comes in because you are trying to convert a single state into a single photon, or maybe or maybe you want to create entangled photons, right? Then you're creating 2 photons. But you're basically always talking about converting single quantum information into single other quantum information. So you need to have a very high conversion rate, very high efficiency, because otherwise you're losing too much information. The other one is about the transfer of the information itself. It says the ability to faithfully transmit flying qubits between specified locations. So this is about, let's say, creating connections, interconnection channels that can transfer quantum information without losing it. So very high efficiency glass fibers that are transferring, for example, photons from one place to another. This is basically the 2 additional ones that go on top of the 5 criteria that we discussed before. And that's basically wrapping up everything that you need to know to be able to build a quantum computer. Now, There's the quantum information theory, which sits on the theoretical side. So they're not looking at the platform. They're just saying, okay, here's a system that fulfills these criteria. And now here's what we can do with it, develop algorithms and so on. There's the physical implementation layer on the other side. So people that are looking for optimized architectures that can fulfill all of these requirements, be it ions, spins, superconducting qubits, Majorana states. What else do we have? Electrons that are trapped on top of liquid helium and being used in terms of their spin properties. So many different ways to actually implement that, and more to come. And combining the two of those then leads to the quantum computers, the successful quantum computing platforms that we might see in the future and that we might already see today. With that, that's everything I wanted to share with you about the DiVincenzo criteria. I hope you liked it. I hope you found it valuable. And I'm looking forward to see you in the next video to talk about another important fundamental concept of physics in the space of quantum technology. Looking forward to see you then. Until then, bye-bye.